All right, section 5.1 for pre-calculus is fundamental trig identities. We started talking about these identities in chapter 4, and we worked on the Pythagorean identities, the reciprocal identities. We also did some quotient identities. There's a few more identities in this list. We've got co-function identities, and then we also have even odd identities. We're going to go through these in some examples today. So you want to have this list handy. Also, we need to note that Pythagorean identities can sometimes be used in radical form, where instead of sine squared equals 1 minus cosine squared u, we could square root both sides and have plus minus. But you cannot square root individual parts, individual terms underneath the square root. You would just have to leave the square root as 1 minus cosine squared. So using identities to evaluate a function. We're going to use the values secant u is equal to negative 3 over 2 and tangent u is greater than 0. And we're going to find all 6 trigonometric functions. So one thing I want to notice is that the secant, which cosine would be the reciprocal of the secant, so negative 2/3. So cosine is negative. That is putting us in one of these two quadrants. And then we also know that tangent is greater than 0. So where tangent would be positive, that's putting us in the third quadrant. So we know that we're in the third quadrant for our theta. So I'm going to use this Pythagorean identity up here that says sine squared, right here. This is sine squared, oops, x, theta, hold on. Sine squared theta is equal to 1 minus cosine squared theta from our last chapter. We're going to use that one. And I'm going to plug in what cosine is. So cosine theta is negative 2/3. And then we're going to square that. And then when I square the negative, it turns positive. So I've got 1 minus 4/9, which is 5/9. So we know that sine squared theta is 5/9. So now I can square root both sides, and I can get sine theta is equal to plus or minus square root of 5 over 3. I just square root the top and the bottom number. Now, because of the quadrant that it's located in, I know that we will be using the negative version of this because sine is negative in the third quadrant. So I will have my sine theta is negative square root 5 over 3. Cosine theta is negative 2/3. And then for my tangent, we're going to use identities for this. So we're going to do our sine theta over our cosine theta. And it was used. I changed it to theta somewhere. I'm sorry. It was used the whole time. It doesn't totally matter, but I apologize. These were all supposed to be used. I'm just going to keep going. I don't want to waste any time. So the sine would be negative square root 5 over 3 divided by negative 2/3. If I divide by a number, I can also multiply by its reciprocal. So negative square root of 5/3 multiplied by negative 3 over 2. 3's cancel, positive square root 5 over 2. Would be the tangent. So our cosecant is 1 over sine. So using just that identity, and that basically means I'm going to reciprocate. So we'll have negative 3 over square root 5, which I can rationalize. Negative 3 square root 5 over 5. The secant they gave us, and then the cotangent is the same thing as 1 over tangent. So I'm just going to reciprocate tangent, just 2 over square root 5, or 2 square root 5 over 5. So this is doing things you've already learned how to do in chapter 4, just using identities instead of labeling a triangle. Example 2, simplify sine x cosine squared x minus sine x. So simplify, we're going to do as much as we can to kind of condense it down, try to get rid of subtraction, combining like terms if there's anything. What I notice here is that both terms are separated by a plus or minus sign. Both terms have a sine x. So I'm going to try factoring. I'm going to factor out that greatest common factor. And when I factor it out, I have sine x multiplied by cosine squared x minus 1. And then cosine squared x minus 1, excuse me, is not an identity above, but I can manipulate it so it is. See, cosine squared x minus 1. Right here, if I take cosine squared x, or cosine squared theta here, cosine squared x, and then I subtract the 1 from both sides. In order to get that by itself, I would have to subtract the sine squared x. So now I have what cosine squared x minus 1 equals. It's equal to negative sine squared x. And then I can multiply these together, and I get negative sine cubed x. And this is as simple as I can go. Another alternate way of doing the same one would be instead of taking out a positive sine x, if you took out a negative sine x here, then you could write the inside as positive 1 minus cosine squared x, which we could go straight to negative sine x multiplied by sine squared x, and then end up with the exact same answer. But I wouldn't necessarily know to take out the negative ahead of time. So either way is fine. Example 3 is factoring the expression. And we've got something squared minus 1. So sometimes you're going to do something called U substitution. U substitution means I'm going to take this letter U and I'm going to say that U is going to represent secant theta. So right here, if I represent U, if I represent secant theta with U, then I can rewrite this as U squared minus 1. And this is a difference of squares. So I'm going to factor the difference of squares, U minus 1, U plus 1. And then I can put secant theta back in. And I have it factored. You do not have to do U substitution if you can see how to factor it straight from the original question to here. That's fine as well. I just showed the U substitution just in case somebody wouldn't necessarily see it right at first. All right, this one over here, it looks like a trinomial. So I could use U substitution if I'm not sure where to go. I'll say that U is equal to tangent theta, and I'm going to substitute that in. So I'll have 4U squared plus U minus 3. So this is a guess and check. I know that we're going to have a plus and a minus sign, one of each. I know that it's got to end with a 3 and a 1, but I'm not sure which one. Actually, I'm going to write the signs after I figure that out. I know it's got to be a 3 and a 1. I have to get a positive 1 in the middle. So most likely I'm going to be multiplying 4 and 1. And 3 and 1 and subtracting them. So 4, that would need to be positive. This would need to be negative. So if I checked my answer, I would get 4u minus 3u, and that equals 1u in the middle. So now if I put my tangent back in, this would be the same thing as 4 tangent theta minus 3 times tangent theta plus 1. Again, you do not have to do this step with the u. You can go straight to the factoring with the tangent in it. It's totally up to you. Right, for this one, we're going to be factoring, but we have a problem because if I use u substitution, these are different things. It does look like it's a trinomial. So at this point, I'm going to look at my identities and see if we have any identities that change cosecant into cotangent. And I just gravitated towards the Pythagorean identities because I have experience using these before. So I knew that there was something to do with that. Here we've got cosecant squared x is equal to 1 plus cotangent squared. Or I'm sorry, theta, not x. 1 plus cotangent squared theta. So I'm going to substitute that. And then I'm going to combine some like terms. I'm going to have cotangent squared x minus cotangent x. And then the 1 minus 3 is minus 2. And I'm going to factor this. And you can use u substitution if you want to try to factor where u is equal to cotangent. You would be factoring u squared minus u minus 2. Or you can go straight to the cotangent. Looks like I'm going to have a 2 and a 1. The middle is negative, so my 2 is going to be the negative and my 1 is going to be the positive. Simplifying a trigonometric expression. So simplifying, again, is going to be rewriting it as simple as we possibly can rewrite it. There are lots of different ways of doing this, and you can't sit there and say, I don't know what to do. You just have to start trying things. One recommended method might be to change everything into terms of sine or cosine. So here I've got sine x plus, I'm going to change this cotangent x into cosine x over sine x. And I'm going to change this, oh, I'm sorry, it's cosine. I'm not going to change it at all. Cosine x. So we have all sine and cosine x. My next step could be to multiply cosine x over sine x multiplied by cosine x. So that'll be cosine squared x over sine x. And we're trying to simplify this, which means I need to get rid of this plus sign. So right now, I've got two fractions. In order to get rid of the plus sign in between them, I'm going to add fractions, which means I need a common denominator. So I'm going to multiply this first fraction by a value of 1. That changes the denominator into sine x. So I'll have sine squared x over sine x plus cosine squared x over sine x. And that's going to give me sine squared x plus cosine squared x over sine x. And then this right here is the Pythagorean identity. That says sine x squared plus, sine squared x plus cosine squared x is 1 over sine x, and 1 over sine x is cosecant x. So you're not necessarily going to know what the answer is going to be until you just start fiddling around with it. And this comes with experience. So you have to try it. You can't just watch me do it a bunch of times and know what to do. You have to try it yourself. Example 6 is adding trigonometric expressions. So perform the addition and simplify. So we look right here and we notice that these are not common denominators. So we want to find a common denominator. I'm going to take, let's see, sine theta over 1 plus cosine theta. And I'm going to multiply that by sine theta over sine theta. And then I've got cosine theta over sine theta, which I'm going to multiply by 1 plus cosine theta over 1 plus cosine theta. So go ahead and multiply straight across. I've got sine squared theta. And then on the bottom, I've got sine theta multiplied by 1 plus cosine theta. I don't know if I need to multiply those out yet, so I'm just going to leave them factored. And then on top here, I've got cosine, and I'm going to go ahead and distribute this one because they're both cosines. So me knowing to distribute it or not knowing to distribute it, that is just something that you're going to try and figure out. I'm honestly just trying something on my own right now. On the bottom, I'm going to leave it separated. Okay, so if they're common denominators, now we can add the numerators. I'm going to slightly rearrange the numerators while I'm adding them because I notice I have a sine squared theta and I have a cosine squared theta on top plus cosine theta. And then on the bottom, I've got sine theta times 1 plus cosine theta. So if I have sine squared theta, this right here, plus cosine squared theta, that is equal to 1 plus cosine theta. And then on the bottom, I've got sine theta times 1 plus cosine theta. Now, right here, I'm saying I am very glad I did not distribute the sine theta on the bottom, because on the top, the entire term, or the entire, the entire numerator is 1 plus cosine theta. And then I have a factor of the bottom that is 1 plus cosine theta. So those will cancel each other out. And I still have a 1 up top, and then over sine theta, which is cosecant theta. Again, these are things that are not going to just come natural until you've practiced it a lot. So if it's hard at first, you just got to be patient. You got to keep trying things and ask me questions. All right, the next one is rewrite so that it is not in fractional form. So there are different ways that we could do this. I think I'm going to show you 2 ways. I think I'm going to show you the way that I would, I don't know, I'm going to show you the way the book shows you, and then I'm going to show you just another way. Maybe you can't remember the way the book shows you here. Okay. So we got to make it so it's not a fraction. In order to not be a fraction, I think I'm going to show you a different way first, and then I'll show you the book way. I think that's how I'm going to do it. So I've got 1 over 1 plus sine x. So if I want this to not be a fraction, what I'm going to do is I need to get rid of the denominator. In order to get rid of the denominator, I need to multiply by the reciprocal of the denominator. But I can't do that because it's 2 different terms. So what I'm going to do, nope, that's not going to work. Just kidding. I'm not going to do it that way. I totally changed my mind. I'm going to follow the way the book did it. Okay. I'm going to multiply by a value of 1. And I'm going to multiply by a value 1 that's going to change this 1 plus sine x into a identity that we can recognize. And so since it says 1 plus sine x, and I go back up to my identities, That's a lot like the first Pythagorean identity here. It's a lot like that one. 1 plus sine x. If I could make it into like 1 minus sine squared x, I could replace that with cosine squared x. So in order to do that, I'm going to multiply the top and bottom by 1 minus sine x. This is kind of like in algebra 2 when you multiply by the conjugate of the denominator when we were trying to get rid of radicals in the denominator. You did something like that before. When I multiply the top, I just get 1 minus sine x. But on the bottom, we've got a difference of squares. So the outside is going to be minus sine x. The inside is going to be plus sine x. And then my last term is going to be minus sine squared x. So that cancels out the inner and outside terms. So now I have 1 minus sine x over 1 minus sine squared x. Now I purposely put the 1 minus sine x on top. So do not factor it and cancel it right now. Do not factor it and cancel it right now. What I'm going to do instead is I'm going to replace this with the identity. Gotta remember what we're trying to do is we're trying to get rid of the fraction. So now I have 1 minus sine x on top, and then on the bottom, I have cosine squared x. Replace that with its identity. Excuse me. Okay, what I can do from here is I could take 1 over cosine squared x minus sine x over cosine squared x. I could separate the numerator by basically using good distributive property to distribute that denominator. And then I'm going to take 1 over cosine squared x. I'm going to take this sine x and the cosine squared x, and I'm going to separate it. So it's sine x over cosine x multiplied by cosine, 1 over cosine x, sorry. Okay, and I'm doing that because I know that this will not be a fraction anymore if I use the quotient identity. That's going to end up being cotangent. Nope, I lied, tangent. Tangent. And then 1 over cosine would be secant. And I don't like when I put a dot there. I'm going to erase that. And then 1 over cosine squared x is secant squared x. So this would be an expression that has no fractions in it anymore. I would assume if you factored it, which there's no reason to factor it, but if you factored it, it would also be an answer. Oops, tangent. I assume that would be also an okay answer, but there's no reason to do that extra step. All right, then the very last one, excuse me, is using substitution. And we've got x equals 2 tangent theta, and where theta is between 0 to pi over 2 to express square root 4 plus x squared as a trigonometric function of theta. So if we let x equal 2 tangent theta, what we're going to have is square root 4 plus parenthesis 2 tangent theta squared. And that's going to give me square root of 4 plus 4 tangent squared theta. I can pull the 4 out by factoring. And if I go to my Pythagorean identities, 1 minus tangent squared, I use this one right here. Let's see, 1 minus tangent, oh, I'm sorry, it's 1 plus, I didn't even remember it correctly. 1 plus tangent squared is equal to secant squared theta. So I'm going to substitute that. Oh, it's because I copied it wrong. There we go. 1 plus tangent squared theta is equal to secant squared theta. Now, I was working this in this direction so that I can use my square root. I need perfect squares to take the square root of. So at this point, I have the square root of 4 and the square root of secant squared theta, which is going to be 2 secant theta.